Okay. So, today we're going to finish up chapter 12. Tuesday we will have an open session for any chapter 12 related questions or test related questions that you may have. The test will open on Tuesday, but you don't have to have it done until Friday.
When you say Friday, like Friday now, like at my class time?
You know, let me think. The other section. Let's say Friday at midnight. So that, because the other section's losing its second class period, so I'm trying to keep things even in that way. So Friday at midnight, it'll be done by the weekend, which means I can grade it over the weekend. We can start the next week by talking about it and then moving on to electricity. Cool. Okay. Any questions about anything at all? Comments, questions, concerns? Before we get started today. Okay. Do please ask me time. It's Friday, so let's get moving so we can open on to the weekend. I believe we at least left off showing you this concept. We were talking about how conservation of energy means that when you put energy into a machine to do work, that energy will either be used for work or remain behind in the machine, basically just pointlessly making it warmer. The most common machine we were using an example for was a hydraulic or pneumatic cylinder, much like this one. And the way that that type of machine specifically works is you have some substance contained within the cylinder. If it's hydraulic, it would be a liquid. If it's pneumatic, it would be some type of gas. And as you add thermal energy to that particular part of the system, it will expand when you add energy. As it expands, the cylinder is going to push and displace and do work. This expansion can be related with this sort of series of formulas, which all the things up here are familiar, even if we are using them in new contexts. Remember from previously, work equals force times change in x. In order to do work, you have to push something in a direction, and it has to move in that direction. But force, there's several formulas with force in them. But the one that's being used here is pressure equals force over area. Because there's definitely pressure inside of this pneumatic cylinder here. There's gases that are heated and expanding, exerting pressure on all sides of the cylinder. The cylinder exerts pressure on gas, which means that there's a certain force over the cylinder's surface area. So we can swap this in for force, which would give us pressure times cross-sectional area times delta x equals work. And well, area times delta x is really just change in volume, because the area of the cylinder is not going to be changing. It's designed so that this circular area stays the same, but the top of the cylinder is going to move up and down, which will change the volume. So we arrive at work equals constant pressure times change in volume. This means that a pneumatic system is doing work when the volume expands. So you add thermal energy to this type of cylinder, the gas expands, and it's going to do work out of itself. Excuse me. This particular formula, though, requires not only that the volume expand, but that pressure stays constant. You can do work with a change in pressure, and that's just a little trick here. So, work equals constant V times delta V. And quick sample. Let's say we have a cylinder that is sorry, I used the word valve a few times. The valve and the piston are the same thing in this particular example, I apologize. You're going to heat this 1 liter cylinder valve, which contains air at 1 atmosphere of pressure, and the valve will expand to 1.5 liters. How much work is this piston accomplishing? So work equals constant pressure times change in volume. Constant pressure is going to be 1 atmosphere, or delta V, final minus initial. We increased from 1 to 1.5. And so ultimately our work done will come out to 0.5. So in expanding, the cylinder output 0.5 joules worth of work. Terribly sorry, excuse me. Thank you. They always have to come in at least pairs. At least pairs, usually trios.
Like that mask is hilarious because like if you sneeze and then you didn't move it, it would be like.
Yes.
Have you done that?
Yes. Conceptually, all of these face coverings are meant to hold the sneezes so that the bits don't go flying everywhere. But with this one specifically, it just makes it then impossible for me to see and really exposed for you guys to look at. Frankly, the normal masks, it's the same way, because then you're just trapped in there with the rubies. All that to say, get vaccines, and this thing. Now, did our work, formula tells us 0.5. The question is 0.5 what?
18 per liters. Ton liters.
So yes, what we did was multiply atmospheres times liters. So technically our unit would be ATM times L. That's not, strictly speaking, a joule, which means we need a slight conversion factor to be able to do anything with this. That ratio is 1 ATM per liter is equal to 101.325 joules.
Why is that like the pressure number?
Because the relationship between atmospheres and pascals is 101,325. Meanwhile, the relationship between liters and meters cubed is 1,000.
Oh, 3.
Mm-hmm. So you were very right. You noticed a pattern. And this formula right here is designed to work best in this form, just W equals P delta V. If you are using pascals and meters cubed. It requires no modification if you're using those.
Wait. Like no conversion of units to joules?
Right. If you plug in pascals and meters cubed, the answer will come out natively in joules. However, if you are using liters and atmospheres, which are common units that will show up in your homework, I advise you go ahead and tack the 101.325 on with the footnote that pressure would need to be in ATMs, volume would need to be in liters. So, two slightly different versions of this, very slightly.
Wait, 1 ATM equals how many pascals? So is that the 100,000, 101,000?
Yes, 1 ATM is 101,325. pascals.
So technically, that's like not the answer.
Yeah.
No,
Yeah.
that unit over there is atmospheres times liters, it's not joules. So how many joules should that be?
50.6625.
Very good.
Two five, is that what you said, 662?
I'm just gonna round to there for now. So, straightforward formula. The only trick is the units you plug in and whether or not you're going to want this part added on. Now, most machines, to some degree, will have parts or components that will behave kind of similar to this. And one of the examples I most commonly bring up is train wheels. Piston pushing the wheel forward, but that's not the end of it. Then the piston has to come back in and pull the wheel back, so then it can go forwards again, keep pushing it forwards, and so on and so forth. So most machines operate in a cyclical pattern where it'll do some amount of work in step one and then require a couple of reset steps to get back to this point to do a good job again. These processes tend to take the form of a heat cycle, which is a series of steps wherein these interactions are occurring in different combinations to lead us to the different parts of the step that are each doing different things. So machines that use heat engines have lots of different stages. This is an example, an old example that I borrowed from my assignment. We're going to look at each of these stages to examine how the basics of this machine work. We have, again, a very similar cylinder. In the first stage, the gas will expand at a constant pressure. So, by our rules, is that cylinder going to be doing work in that moment?
Yes.
Yes. Constant pressure and expansion. Positive work done. Very good. We're given units of liters and atmospheres. So we'll tack our little conversion on there. Work equals, why is my note like that? Work equals constant pressure of 6.5 times our change in volume, 3.5 minus 1, times our conversion into joules.
Line 646.53.
Very good. Sorry, can you repeat the decimals?
1653.
Thank you. All right. So in this moment, the machine did work. It built it to do something, and it did the thing. But once that cylinder is extended, something needs to happen to set it back. Now, if this was the cylinder within the machine in question, and it expands and it does work and it expands, it needs to be reset. Would it really be worth our time for a different machine or for a person to come in and just recompress it as it currently is? No. If we went in reverse and say, at the same pressure, just went from the new volume back to the old volume, at best, the process would just put all the energy back inside of this thing. It would be the same amount of work put into the machine and unaccomplish whatever we just accomplished. So typically what will happen is the system will be designed to lower the pressure of the cylinder and then reset it. Because once the pressure is lower, it takes less work to reset it, then you repressurize it, and then it goes again.
Wait, they do that by cooling it?
Cooling it, sometimes changing the amount of material inside of it, like letting it vent and then refilling it later. But oftentimes it'll be cooling. So, in this particular step where the pressure is dropping, the volume stays constant. So in this moment, is the piston doing work? No. Why?
Because it's a constant volume?
Good. Constant volume, it means delta V is 0. So whatever happens in pressure, we've already got 0 work being done from the cylinder's perspective. So this part is 0. Excuse me. Next step, after we reduce the pressure, hold that new pressure constant as we then contract the cylinder. Is work being done here?
Wait, but it's negative.
It is negative. Which means that some other thing is doing work on the cylinder to reset it. We arrive at that negative because we have W equals our new pressure of 1.5 times. We're going from a volume of 3.5 back to 1. That's dropping, so our work will end up being negative. I don't remember the number off the top of my head. I think it's 400 something.
Negative 379.97.
Thank you. 97?
Yes.
So in this step, energy had to be used by something else to do work on the cylinder and reset it. So in this moment, something else needs energy to actually do this. So it's becoming an increasingly more complicated machine. You now need a component that can do this to the cylinder and then re-pressurize the cylinder so it can do this again.
How do they compress the gas?
Frequently either cooling it or some other machine pressing on it.
Well, like, if you press on it, you increase the pressure, and don't you want to?
Oh, yes, sorry. Decreasing pressure would involve either cooling it or releasing material.
Oh, that's what you were talking about, the venting thing, right? Yeah, okay.
And the next step, now that we have obtained our reduced volume, our pressure is going to go back up at constant volume. So is any work being done here by the cylinder?
Yeah.
None. Constant volume means nothing. So, all 4 of these steps form the cycle of this particular heat engine. And to find the net work accomplished by this particular machine, we just want to add every step together. Keeping careful of the signs though, a big positive, 2 zeros, and 1 small negative.
1,266.56, but.
Wait, that, this, the second two are missing.
Oh, sorry.
Yeah.
You repeat the whole thing.
1,266.56.
Okay. I was misremembering. Finite. Okay. I was conflating some memories from the last time I did this one. So, overall for this machine, we have a net positive, which is good. Usually we have a large amount of thermal energy to spend, and we need it to do an amount of work from that thermal energy. So this machine is doing the work, very good. And oftentimes, these heat engines will be visualized with graphs. And so, I'm going to very quickly draw a pressure versus volume graph. Our beginning step saw us at high pressure, the higher end of the pressure, as the volume increased from a smaller number to a bigger number. And as the pressure was constant that whole time, that's just going to form a solid line. Actually, I should write. That was step one. And the arrows just represent the direction. In step two, pressure dropped while volume remained constant. So that's going to work. A line straight down. Third step, volume decreased while pressure stayed constant, this new low value. And lastly, pressure increased while volume was constant. This describes our heat cycle. What's convenient about visualizing it like this is, this whole time all we've been doing is really multiplying pressure by changing volume. So this final answer here, the total work done by the machine, is the area of the box. The two vertical sides don't contribute anything to area or finding it, like area under the curve style. If we just look at the top part here, the step where we actually accomplish the most work, the area just under that curve would stretch all the way down to 0 and would be equal to this number. But then, when we factor in part 3, it was doing negative work, and hence the arrow. It's there to help indicate that we would subtract this chunk out from the first step to get the air boxed area. All heat cycles can be represented like this. Most machines can be represented like this. And once you are able to use this type of a graph, it becomes easier when the situation gets stranger. This formula is great for when the pressure stays the same. Sometimes it doesn't always stay the same. Because very often, say, if we were looking at the piston driving train tracks, that piston extends, contracts, just repeatedly. It doesn't stop. Depressurize, contract, repressurize, and then come back out. It's just smooth and pretty instant. So that particular graph would probably look more like this. You've got one fell swoop for doing the work, and then one return stroke where it's not doing the work.
What formula do you use for them?
Well, you would need to know the equation for each of these lines. You could probably take a derivation and ultimately just solve for the area crescent shape, I would not ask you to do that
Oh.
because I don't like that. But what I might ask, a type of graph that you might actually see that I might have you put numbers to, is instead of a crescent shape, you reduce it to a triangle. Which is a geometric shape that you can more easily find the area of. So for situations where pressure stays constant, this formula works. But this formula just really helps to build this visual, which having the visual can help if pressure is not always constant. I'm not going to ask you to do the crescent thing.
So like, you could give us the graph of the triangle thing and ask us to find the total work done by this thing, right? And then you would do the area of the curve from like the 1 down, all the way down, and then 2 down, and then you subtract.
Yes. You would solve for the work done in step 1 by just finding area under the curve, which would be this triangle plus the box fitting thing.
How do you do that again? Oh, wait, oh, are you given like little squares?
Squares, and you would also, in this case, know, say, what the numbers on the graph are.
Oh, okay.
So for this particular triangle, this leg goes from 1 to 3, this one goes from 1 to 2. So that's going to be a difference of 1 times a difference of 2. So if it was a square, that would be an area of 2, but it's half a square, so it's just 1.
Oh,
So geometry
Okay.
time.
we did that in calculus.
Sorry, I didn't put the numbers on there the first time. So fun fact, the legend that I've been told is that calculus was invented to do physics. That's the reason it exists. So, yes, I'm trying to keep to the algebra mostly, but calculus applies to all this. Calculus is usually how we got most of these formulas in the first place. Okay. All of that from yesterday and today can be filed away under the first law of thermodynamics. Let's finish up by looking just a little more closely at the second 2 laws of thermodynamics. Okay, first, any questions before we move on? Okay. There's only 2 laws left, and very little. So let's get to it. Second law of thermodynamics. The grand definition tells us that the entropy level of the universe is constantly either staying constant at best or rising at everything else. What this means for the sake of this class and your daily existence is every single process where one object is moving and touching another object, there's going to be some amount of friction. Some energy is going to be lost to thermal energy. This is where the entropy rise comes from. If I lift a box and I do 10 joules worth of work, my body technically had to spend more than 10 joules, because if I only used 10 joules, half of that would get eaten up by friction, and I'd only do 5 joules worth of work. So depending on the efficiency of my body, say if my body is 50% efficient, If I wanted to perform a 10 joule task, I would need to spend 20 joules. 10 of the joules would accomplish their purpose. The other 10 would be turned into thermal energy, which is now trapped in the matter of my body and slowly vented into the atmosphere, simply increasing the entropy of me and my surroundings. If you had a process that was 100% efficient, all the energy in was used and none of it became thermal energy, theoretically in that moment, entropy levels would stay constant. That would be an ideal reversible process where you can just keep doing it back and forth and there's no thermal energy increase. However, literally everything ever has been a spontaneous real process where some amount of thermal energy is created. Even drifting through the vacuum of space will create some amount of thermal energy because you will be striking cosmic dust as you go, and eventually the solar wind. What that means is pretty much every real process that you can ever perform in the real universe can never be perfectly reversed if it can be reversed at all. This is the literal textbook example of that. And what this means for machines is every single thing a machine does will take some amount of energy. This is especially egregious when it comes to air conditioners, because if, say, the point of the air conditioner is to remove 10 joules of thermal energy from the air of this room and send it somewhere else, it still costs energy to do that. The machine doing that movement will burn energy to do it. So if you want to move 10 joules, it'll cost you 20. Every single thing does it, and it's really annoying. For every single machine, that means it has some efficiency rating, which is just the percentage of output to input. If you give a machine 10 joules and it does 5 joules worth of work, the output is 5, the input is 10, that's going to be 50% efficient, which would be revolutionary actually, because most high-end machines top out at about 20%. And that includes your own body. The official variable for efficiency is nth. I don't actually know the story behind that one. Nth equals output over input. It's just the percentage, the ratio. And because it's a ratio, it doesn't itself have a unit. If you just do the fraction, you just get a small decimal value with no unit on it, but you can then turn it into a percentage.
So you're saying that because everything is not like ideally efficient, like perfectly efficient, that means that the entropy of the universe is always increasing because...
If we examine the entire universe as a whole, just looking at all the thermal energy that's inside of it and all the entropy that's inside of it, every single thing within the cosmic bubble, yes, every single process, more and more energy is slowly converted into thermal, which just raises the net temperature of the universe, which just increases total universal entropy. Every time you move your muscles, this happens. Which means We can't avoid it, so I try not to worry about it. It's just a byproduct of being alive.
So like entropy is like, you know, randomness, right? So
Mhm.
why is increasing the temperature increasing randomly?
When particles have thermal energy, they move, and they will bounce off of each other repeatedly.
Oh, okay, yes.
So the higher the temperature, the faster they're moving, the more they're colliding, the more random this movement is. So yes, high temperature directly correlates to high entropy, which will lead into the third law of thermodynamics. So, quick sample. We have a machine. This particular machine requires 10,000 joules in order to work. Once we feed it that energy, it does its task. At 5 atmospheres of pressure, it will expand from 2 liters to 5 liters. What is this system's efficiency? Efficiency is going to be out over in. We're told to be in, straight out, 10,000 joules. So how much output does this machine do with that?
Don't you just use a formula?
Yes.
Work.
We need to know how much work this machine does. We have a formula for work where volume expands and pressure is constant. So our constant pressure is 5 atmospheres. Our volume expands from 2 to 5. We're going to tack on our little conversion ratio there. So what would our inf ratio be?
About 0.152.
Very good. And that would amount to this machine being about 15% efficient, which, again, compared to most processes in the universe, isn't half bad. If a human body operates at 20% efficiency, it's just south of that, and that's a lot better than, well, any machine where gears are grinding against each other. So every real machine in the real universe will have some inf between 0 and hypothetically 1. If you can create a machine with an inf of 1 and efficiency of 100%, call me, it'll save the world. If you can somehow create a machine with an inf higher than 1, you've broken physics, and we need to know about it immediately. Because that machine would put out more energy than it had. Which would probably be a fusion reactor.
Wait, are you like breaking, like, you know, energy cannot be created nor destroyed, like, aren't you breaking that concept?
Yes, absolutely. If you had a machine that output more energy than you put into it, you'd be either violating the law of conservation of energy, or you would be a star.
Because like in reactions, it can seem like there was more energy as a result, but that was just like stored like potential energy within, or chemical energy within like the compound. So like it wasn't really.
Correct. The energy was present, just not in a readily available kinetic or thermal form. This is prevalent with chemical reactions, and after the reaction is spent, that energy is spent, the reactants can't do it again. It's a very similar thing if you look at stars and suns, because they operate off nuclear fusion, not nuclear fission. Actually, nuclear fission is a pretty good example too, because when you split an atom, you take all the energy that was inside the atom and just release it all in one fell swoop. Meanwhile, a fusion engine involves taking two small particles and jamming them together to create a bigger one. It's the opposite of fission. And that makes it look like you're getting more energy than you put into it. It takes some amount of energy to jam them together, and the output should be more than the input, but that energy was stored in the particles to begin with, and now that it's released, you can't put it back. That happens because while energy can't be created or destroyed and matter can't be created or destroyed, the reason both of those laws go hand in hand is because energy and matter are the same thing. Matter is highly compressed energy, which is why you can break matter to get more energy. But once it's energy, you can't make it matter again. Not with any technology we have.
Wait, what? Really?
When like fission and fusion happen or work, because in a fission reaction, at least one of the subatomic particles present inside of the atom physically ruptures and breaks down. Some of that particle might become other smaller particles, but some of that matter literally becomes energy. Matter and energy are two different states of the same thing.
So the reason why we can create things is just because we have that much matter in the universe. And so like technically if we were to end, like there'd be no more matter, there'd be no more energy, thus death.
The heat death of the universe is the point where all energy has become thermal energy.
Yeah.
There's no other potential or kinetic energy left besides thermal. And I assume at that point all matter would have broken down into thermal energy too, which means that the universe would just be an empty void, and a hot, empty, buzzing void. Of course, if you have no matter, you have no matter to possess the thermal energy, so that's a little bit of a paradox. And I'm pretty sure that the rapture will happen before that point. Some apocalypse or another. Okay, so all machines have efficiency. Pretty easy to calculate. Last law of thermodynamics, we're talking about entropy and heat death of the universe. Third law of thermodynamics. Entropy is directly, or the entropy of one thing is directly tied to the temperature of that thing. The hotter one object is, the higher that object's entropy level is. You can reduce the random movement of a specific object by reducing its temperature. And hypothetically, if you can reduce an entire object's temperature to absolute zero, it should at that moment have zero entropy. Because at absolute zero, the particle shouldn't be moving anymore. No movement means no randomness. No randomness means no entropy. But even if you could do that, you'd simply be siphoning the thermal energy out of that object, and it would have to then go somewhere else. Which again, the net entropy of the entire universe would either stay constant in that, because now that entropy is in another object, or it would rise because you needed to spend energy to move that thermal energy around. Because all air conditioners cost something. So you can reduce one object's entropy. The universes will still go up. Sorry, I don't know what that was. And those are the laws of thermodynamics. Only math tied into what you want to use on the homework quiz.
Wait, how do I,
There's no formula.
like what kind of question would I be given related to the third law?
I'm not planning any for the homework test. but it is a law and it has concepts that are important to know. The other laws contribute more than math in this chapter.
Did you say that reaching absolute zero is like impossible naturally? Like it has to be under,
It is impossible naturally because most matter tends to be touching other matter. And through that contact, you'll just get more energy. If you're trying to cool object A down to absolute zero, as long as it's touching the table, even if I'm siphoning as much energy as I can out of the top, it'll just gain more energy through the table.
then how do you even do it at all? Do you have floating things?
You would do it to single particles, like single protons with lasers in an empty space. Because all particles are vibrating at a specific frequency, very smart people have figured out how to use lasers of the same frequency as little subatomic tractor beams to literally grab a particle and force it to hold still. And once it's still, it stays still until something else touches it. As soon as any other particle bumps it, it warms back up, which makes it really, really hard to get more than one atom at a time at absolute zero. That said, we've tried, and if an actual object was at absolute zero, like an actual collection of particles, things would get really weird because the particles shouldn't be moving, but they're now so close together that their quantum wavelengths have started overlapping, and it becomes a weird, soupy, timey-wimey mess. Which is why I'm kind of glad it doesn't happen in nature, because I don't know what that would look like. So, work on the 12 homework over the weekend. Send me questions, come prepared with questions. We will spend most of Tuesday going over all the things related to that, and then reviewing, tying things together for the test, which you don't have to do on Tuesday. You'll have it till the end of the week. Any questions?
Wait, what are your hours again? Like,
My office hours?
yeah.
If it's test time, I'm accepting emails until I am asleep.
Okay.
That said, try to take the test during daylight hours where I'm more likely to be awake. Thank you all, and do please have a good weekend.